Hello and welcome to the Daily Space for today, November 27th, 2018. My name is Dr. Pamela Gay and I am here to put science in your brain. Now, today we have a whole variety of different stories that we're going to bring you, but before I do that, I just wanted to say thank you for being here. Give our channel a follow if you like what you see. Follows are free and it will let you know whenever we go live. Miss a live show? That's okay. Everything we do here gets archived over on YouTube. And for those of you watching on YouTube, you can watch this show live over on twitch.tv/CosmoQuestX. Now, today we have a variety of stories to bring you. And the first one, well, if you haven't already heard this, you live somewhere where you haven't got a lot of news. Yesterday, NASA landed a new robot on Mars. This is the InSight lander. It is a spacecraft that has been deployed to measure, well, the passage of quakes and waves through the surface and interior of the red planet. Using a seismometer that it will deploy in the coming weeks, it is going to help us map out the interior of Mars and answer questions about, well, just what was the history of Mars' magnetic field and how cold is it and how solid is it on the inside of the red planet. In addition to deploying the seismometer, we are also going to deploy a thermal detector that is going to thump its way one hammer stroke at a time meters in to the Martian surface. This thermal detector is going to allow us to understand just how much heat gets caught up underneath the surface of Mars, trapped there, and perhaps allowing liquid water and maybe even life to exist, well, beneath that too cold, too vacuumy surface. Now, we have already started to get some initial images back. This is the first really good image that we've gotten. It is taken looking out at the area around the lander. You can see that closest to the lander is some nice flat sandy surface or some rocks off in the distance. This is exactly the kind of boring area they were hoping to put this spacecraft. The goal here isn't to examine rocks. It isn't to do anything exciting. It is to systematically lower down that seismograph, systematically bore down that thermometer and see what's inside, which hopefully in this case will be all the excitement we need. Now, InSight didn't travel to the red planet alone. Accompanying it was a pair of 6-unit CubeSats that, well, were about the size of suitcases. These two interplanetary explorers didn't have the engines they needed to put themselves in orbit around Mars as InSight went in for a landing. Instead, they did a flyby. But this flyby was an amazing test bed for us to see just what CubeSats are capable of. These two missions were able to relay back to us real-time information on InSight as it did that landing and as it settled in on the surface. It was the first spacecraft to let us know everything was A-okay. Now, these two little spacecraft are still out there. They're still continuing their journey around the sun. They're in heliocentric orbits that will continue taking them on paths that bring them closest to Earth's orbit, closest to Mars' orbit, but neither planet is in jeopardy of getting visited by these two little spacecraft in the future. Now, what this tells us is someday, when we're able to send more landers and more rovers to more worlds, we may not need to worry as much about having heavy-duty communications rigs on the landers and rovers. It may be that we can simply upgrade our CubeSats and get them to be those orbiting relay stations that we rely on so heavily with Mars today. It was actually Mars Odyssey, which got to the red planet in 2001 that sent us back the bulk of the information from Mars Insight. It was the mission that told us, yes, the solar panels did deploy successfully. Now, this is just a start, and it's up to creative engineers around the world to figure out exactly what the future brings for this now proven technology. Now, moving a little bit further afield, I bring you news of massive Earths and potential new ways of forming magnetic fields on these distant worlds. One of the things that we've been discovering is planets come in formats we had never imagined, well, prior to seeing them. It turns out that there are rocky worlds many times bigger than Earth. There are Jupiters in every possible configuration orbiting a star. And as we try and understand where is it that we might be able to find life out there among the stars, theoretical planetary scientists have been working to build up computer models that simulate all the heat flow, all of the internal dynamics of these worlds. In a newly completed set of models worked on at the University of California, Berkeley, planetary scientists have determined that in massive Earth-like worlds, it's possible that the silica mantle of the planet will stay molten, will stay convecting, circulating much longer than it did here on our own planet Earth. Now, with this convection, their models have gone on further to show that these silicate materials are capable of becoming charged. They're capable of conducting electrons in a way that allows them through their motion to generate strong magnetic fields. In our own Earth, the silica mantle is largely solid, and it's our iron core, the outer layers of our iron core, that is actively convecting, that is actively generating our Earth's magnetic field. Now, with these super Earths, with this molten silica mantle that stays molten for so much longer because the worlds are so much bigger, and just like a big pie takes longer to cool off than a little pie, as many of us in America experienced last week, big planets take longer to cool off than little planets. And these big worlds, with their big molten silica mantles, as these mantles circulate, will be generating big magnetic fields. Now, the reason that this is so exciting is we know that life can be helped out by the presence of a magnetic field around a world. Magnetic fields have the effect of, well, deterring, bending away, blocking many of the high energy particles that come flying at us from the sun. Interactions with these particles can, well, transfer momentum to lighter weight molecules, lighter weight atoms, and send them flying at escape velocities, slowly stripping off the atmosphere of a planet. This, unfortunately, has been the fate of Mars, which, because it's smaller, has already cooled off and lost its magnetic field. In the past, it too had a magnetic field. In the past, it had a warm, wet atmosphere and surface. With the loss of that magnetic field, it also lost a lot of its atmosphere. Its lack of gravity also helped. Now, we understand that these massive worlds likely have massive magnetic fields, which will mean all the more protection for high energy particles coming in at the atmospheres of these worlds. This also has interesting implications for our own planet Earth. Back in the past, when our world was still pretty much a molten lump in the early solar system, we probably had these extra magnetic fields as well. In our case, we were also a bit squishy and soft at the time as a planet and probably weren't very conducive to the evolution of life. But it's still interesting to think that early on in the solar system, our world was physically a very different place with very different, not just surface structures, but internal structures and magnetic fields. Now, continuing our journey outwards, I bring you news from the Australian National University. In research led by Roland Crocker, astronomers have worked to try and understand how it is that star formation in clusters is slowed down, preventing all the stars from forming in one massive burst of formation, and in the process, limiting the formation of planets. Currently, when we look out at star forming regions, such as the one shown in this image, we see young stars, massive hot stars, the blue stars in this image. But we don't see all the stars forming at once. We see them forming over time. We see knots of gas. And the question is, if gravity caused the cloud to begin to collapse, if it has started to fragment into chunks that form stars, why didn't all of it just form stars all at once? And this is one of those things that it seems like it should be easy to solve, but it took time and modeling and careful looking to realize that, well, the biggest stars form first because the gravity there is massive. You have a big clump of gas. It contracts quickly because big acceleration, because big gravity and big clump of gas. But then the light pressure from that young star, light exerts pressure. The light from your lamps is pushing on your skin right now. You just can't perceive it because, well, the air pressure is much greater. But when you're looking at the amount of light coming from young stars instead of the amount of light coming from lamps, that light pressure is enough to slow the collapse of these star-forming regions, to slow the formation of those smaller stars. And it's because of this light pressure slowing down the collapse that we see the star formation stretched out over long periods of time. And when those first young stars finish living and start dying as supernova, they don't destroy all the young planetary systems because not all those systems have formed yet. They don't sterilize the entire system. This slowing down allows the angry young stars to essentially terrorize a bunch of gas instead of terrorizing a bunch of young planetary systems, thus allowing, in the fullness of time, for those smaller stars to eventually end up forming, and eventually, potentially, end up forming life. So those are our main news stories for today. But before I go to taking your questions, I do want to say today is, well, here in the United States, we refer to it as Givingtuesday. This is a day where after everyone has gone out shopping at the big box stores on Black Friday, after everyone has shopped local on Small Business Saturday, after people have done whatever they do on Sunday, after they've bought everything else on Cyber Monday, if you have anything left, it's Givingtuesday. CosmoQuest is supported through your donations, through your subscriptions here on Twitch, through your Patreon giving, and beneath this video, you can find all the different ways that you can support everything we do. This year, your contributions are more important than ever. We'd been warned several months ago that due to cost overruns with the James Webb Space Telescope and changes in policy, there was a chance we might be losing the funding that we use for our day-to-day activities that pays for the students and mostly early career staff that make CosmoQuest happen. Now, unfortunately, those funding cuts came through, and we are now trying to bring in enough funding to bridge us until either we can get a new federal grant or we can make sure everyone has a new job. And we're asking for your help to make that happen. I've given what I can, and I'm going to personally step back and make sure that your contributions support, well, the younger people and the people who day to day need the job. I would ask that if you have anything to give, that you consider giving it to science. Okay, I hate fundraising. Please give so that I can do science instead of begging for money. I'm now going to take your questions in the chat, and thank you all for being here. Okay, so let's see what questions we have. So Veronica Cure is asking, will Patreon subscriptions need to be updated with the organization change? No. One of the great things about Patreon is we can go in through the back end and redirect the PayPal so that the new organization, CosmoQuest, is now out of the Planetary Science Institute. We took care of absolutely everything, and you don't need to worry about it. So thank you, Veronica, for asking. Okay, let's see what other questions are out there. Hey, Average Joe, thank you so much for being here. I don't think I've seen your name recently. So many new names out there. This is awesome. Thank you all for being here. Looking to see if there's any questions, scrolling back. If you can @ me, I would really appreciate it because there's a lot of chat going on and that will help me find your questions. For now, I'm just looking for question marks. So Larry asks, how long will Marco A and B be able to transmit? I actually don't know the answer to that. They have solar panels. There's no reason for them to stop transmitting. But spacecraft in general only have so long that they're able to live. I'm not sure what the expected lifetime of these spacecraft are. That may in fact be part of the question we're working to ask with these missions. As always, scientists want to know everything, but we don't. And sometimes we just have to say, don't know. Okay, that's all the questions I was seeing up above. It's okay, Star Song. We fully understand. And there's ways that you can support our programs that aren't just about donating money. Help get the word out. Help get other people here. Help get other people involved in science. That, in many ways, is just as important to us. And we're a citizen science project, going over to CosmoQuest.org and contributing to science, to helping to map out craters, to helping us figure out what is on the surfaces of these other worlds so that we can keep finding the safe places to land and the interesting places to explore. This is our core mission. This is why we want to be here. This is why we want you here. Help us science. That is what matters the most to me. Unfortunately, it just takes money to do science, and that is something that is not the favorite thing in my day. Anyways, so other questions out there. So while you're typing those questions in, tomorrow I will be back the same bat time, the same bat channel. The background may be different. I'm going to be up at Illinois College giving talks both tonight and tomorrow night before returning. So you may not have the same background, but you will have the same broadcaster. Thank you so much. We will keep bringing you the science. I'm not seeing any more questions. Astronomers are only 1 in 1 million on the planet Earth. You have one sitting here willing to answer your questions. They don't have to be just about today's news. Feel free to ask me anything astronomy related. Back at you, Fenring. So Paranor is asking, do you know when InSight will start its drilling? They're always non-specific about this. And for drilling, I'm assuming you mean the hammering in of the thermal probe. What I've been hearing is this is going to happen in the next several weeks. The vagueness on this is they could look around and realize, wow, everything around is absolutely perfect. We have no trouble. We can thump in anywhere we wish. Or they'll look around and be like, huh, okay, this looks like a complicated surface. We're going to need to think about it. Once they have a better understanding of the surface around the spacecraft, then they'll be able to, well, have more firm dates on when we can start putting the thermal probe into Mars. So Ben Sign Games is asking, so what will the InSight probe discover? Well, the primary mission is it's going to figure out what the thermal structure is in the uppermost layer of Mars. For my entire adult professional life, I've been going to meetings and hearing talks where various geophysicists and planetary scientists say, well, it might be that 20 centimeters under the surface, it's this temperature. It could be it's this temperature. And the idea is that underneath the surface, it's able to retain heat a little bit better, perhaps allowing liquid water to exist. This probe is finally going to allow us to know what that thermal profile is, what that temperature as a function of depth beneath the surface is. Now, beyond that, when waves move through worlds, they bend around different densities. We have two different major kinds of waves that move through planets when there's some sort of a quake, either caused through natural geologic activity, caused by landslides, caused by, well, with Mars, they get rock impacts as meteorites strike the surface. All these different things that can shake the red planet generate waves that move through the world. There's two kinds of waves: primary waves, P waves, that are compression waves. As they move, they compress the particles together, moving in a lot of ways like acoustic waves do through the air. These P waves are able to move both through solids and liquids as they pass through the planet. The other kind of waves, S waves, secondary waves, these are oscillatory waves, and they can't go through liquids. They can only go through solids. By looking at how these two different kinds of waves move through the world, they can map out where is their liquid, where is their solid, and how exactly do all of these structures map together. This is the other part of what InSight is going to be doing, mapping out the interior of the red planet. So scrolling up to see what other questions there are. Larry, I haven't read about the VSL, so I'm gonna not answer that. So Veronica Cure is asking, what citizen science projects are currently available at CosmoQuest? Oh, variable speed of light, Larry. I'll come back to that. So currently we have projects for mapping the surfaces of rocky worlds. You'll see Vesta there. Vesta's actually finished. She'll be coming down on January 1, and hopefully we'll have a new project going up, but I can't tell you what the project is yet. It's going to have to be a New Year's Day surprise. Beyond mapping out Vesta, which we're done with, we also have a project to map out the moon, where we're looking at, I believe it's the region around Apollo 15's landing site, to very carefully age date that region. And that data is actually getting used also to train computer deep machine learning algorithms. The moon is so big that we'll never be able to get a highly detailed map unless we can get the computers to do it for us. So we're trying to get the humans to do it for a small region. And then we'll get the machines to take over, using your citizen science data to train those machines. We also have projects to look at Mercury, where we're trying to study exactly which of the craters are created by space rocks hitting Mercury, and which are created when those impacts, those primary impacts, hurl boulders up that then cause secondary impacts further out on the surface. We're also working to map out Mars. They're trying to understand where different craters have, well, caused splash zones around the impact site and have had other interesting dynamic features generated. Always there's something new, and stay tuned for more things to be added. So Prof. Melko is asking, how do they know the core is totally solid? So they don't know if it's totally solid, and this is why we have insight. There are some theorists who predict that there are pockets that are still potentially liquid inside Mars, but the primary evidence for Mars not being completely liquid is there doesn't appear to be active volcanism, and Mars doesn't have a strong currently generated magnetic field, although we see relic magnetic fields in the surface. So areas of rock capable of holding a magnetic field that formed when Mars had a magnetic field continue to have that magnetic field. It's just a new magnetic field isn't still being generated. So with the lack of volcanoes and with the lack of present modern day magnetic field, we think it's at least mostly solid. So let me see what else. So Larry is asking, do you think InSight could find underground liquid water? We don't actually know. So here's the reason. No, the answer is it probably won't. It probably can't. You always have to add caveats with Mars, though, because there's always that one in large number chance that we're going to realize as it digs in that it hit a layer of briny, wet soil. That's probably not going to happen. It's really, really probably not going to happen. But there's a non-zero chance that it could, so I'm not going to say it's not going to happen, but it's probably not going to happen. Oh, Ben, Science and Games, what did you put? When is the earliest launch date for a manned mission to Mars? So fusion drives don't exist. Antimatter drives don't exist. Currently, the best way for a human being to get to Mars is with our standard propulsion systems. We have the technology to get to Mars using that today. If you're not worried about keeping your astronauts, alive. The problem is that our sun likes to periodically throw out massive ejections of high energy particles and extreme radiation. These coronal mass ejections, should one hit a manned flight on its way to Mars, without proper shielding, would kill everyone on board, and it wouldn't be an easy death. So until we figure out how in a cost-effective way to deal with those issues, we're kind of stuck. But I have confidence that we will solve these problems. My guess is it's probably going to be the 2040s or 2050s before we start sending men to the moon, and hopefully women too. But I'm being reminded I'm supposed to be in a meeting. Yes, Veronica, InSight is as sterile as we could get it. It's not perfect. It also landed someplace where we don't expect there to be life. And I will answer more of your questions tomorrow when I come back, once again, at 1 p.m. Eastern, 6 p.m. London, 10 a.m. Pacific, and bring you the daily news right here at CosmoQuest. And I just want to thank all of you once again for being here and supporting our show and, helping